So it's a pleasure to introduce the speaker of today, Mar Mezcua from the Institute of Space Sciences in Barcelona, in Spain. So Mar is an expert of high energy astrophysics observations. She has done her PhD in Bonn at the Max Planck for radioastronomy in 2011, I believe. And then after that, she have moved quite a lot for postdoctoral fellowships around the world. She was first at the Canary Islands in La Laguna, then she went to Harvard, to CFA, and then after that she was in Montreal. And then in 2017, she came back to her home country, to Spain, and she settled at the Institute of Space Sciences, where she has been since then, and she also had a few fellowships on the way while there. So Mara has been the PI of a number of important observational programs, for example, some with Chandra, which have been pioneering the discovery and study of low luminosity AGNs in dwarf galaxies, and also the search for intermediate mass black holes. Actually, the two topics are quite connected. She's also worked a lot on ultraluminous X-ray sources, which are also believed to be connected to at least some intermediate mass black holes. And so it's really a pleasure to have her speaking today about the seeds of the first supermassive black holes.
Okay, no, thank you so much, Lucio, for the introduction, the presentation, and for being here finally after 2 years of trying to come. I'm so glad I finally made it. So yeah, I'll be talking about the seeds of the first supermassive black holes. This includes several projects that I've been leading and also in collaboration with many people, as you can see here. Most of these projects are observational, so I'll try to give an introduction, a broad introduction to the topic for those who are not experts in the field. And afterwards, you can ask me, of course, many questions, and with many of you I'm meeting afterwards, so we can also discuss possible ideas. So I'll start with an introduction to black holes. Now, from on the lowest mass regime, we have stellar mass black holes, which, as you know, come from stellar evolution, from the death of massive stars. And these have, according to theoretical models, up to 100 solar masses. Now, and then in the other end, we have supermassive black holes of more than 1 million solar masses, most of which reside at the center of massive galaxies. We think that most massive galaxies have a supermassive black hole at the center. Then we know there's a current stability gap here in between 140 and 260 solar masses where no black hole should be formed. And in between the two regimes, we have intermediate mass black holes. So we expect black holes of masses higher than those from stellar mass, so above 100 solar masses, but below those of supermassive, so below 10 to the 6 solar masses. That's why these are called intermediate mass black holes. And what's most important is that we think these intermediate mass black holes are the seeds from which supermassive black holes form and grow. Why is this important? Because, as I said, we think that most massive galaxies have a supermassive black hole at their center. When this supermassive black hole is actively accreting, we call it AGN, active galactic nucleus. And we think that AGN can expel winds, and these winds can impact the host galaxy in which rays reside. Not only impact, but regulate the host galaxy, the formation of stars in the host galaxy. So we think that supermassive black holes and their host galaxies co-evolve, grow together, grow in tandem. And this is based mainly on the finding of some black hole galaxy scaling relations. On the y-axis, we have black hole mass. On the x-axis, these are host galaxy properties, such as the luminosity of the bulge or the stellar velocity dispersion. This one here is the M sigma correlation. It's a very famous one. You see, it goes all the way from 10 to the 6 solar masses to up to 10 to the 10 solar masses. So this is one of the tightest correlation between black holes and galaxies. These correlations have been mostly found in the local universe. However, we have been detecting quasars, so supermassive black holes of up to 10 to the 9 to 10 to the 10 solar masses at very high redshift, redshift 6 to 7. So when the universe was less than 1 gigayear old. And in this summary from Rosa Valiante, we can see this is the redshift record holder of a quasar or a supermassive black hole, an active supermassive black hole at redshift 7.6. And this is the largest black hole mass of 10 to the 10, also at a redshift 6 point something. The problem is that these supermassive black holes, so massive, of up to 10 to the 10 solar masses, when the universe was less than 1 gigayear old, the supermassive black holes didn't have time to grow from a stellar mass black hole. Okay, in less than 1 gigayear, you cannot have a stellar mass black hole grow from, let's say, 50 solar masses to 10 to the 9 solar masses. Okay? That's why we have to invoke lower mass seed black holes, intermediate mass black holes, often between 100, 10 to the 5, 10 to the 6 solar masses, from which via accretion and mergers, you can grow and become supermassive. So the question that arises now is, how do these seed intermediate mass black holes form? And this is a summary sketch that I published in a review in 2017, where we have here redshift, this is black hole mass. These are the supermassive black holes that we find in the local universe and up to redshift 6 to 7, with 10 to the 9, up to 10 to the 10 solar masses. And these are the seed black holes that can form at high redshifts, about redshifts 8 or 10, via mainly 3 mechanisms. One of them is that these seed black holes from the death of the first generation of very massive stars, of population 3 stars. These light seed black holes, because they form from these top 3 stars, should have around 100 solar masses. We can also have formation of seed black holes via mergers in nuclear clusters in the early universe. And here the seed black hole would have a mass of around 10 to the 3 solar masses. And then we can have heavy seed black holes formed via direct collapse, these ones here. And these can have 10 to the 4 to 10 to the 5 solar masses. Okay. Now, all these seed black holes should have time to grow and become supermassive by redshift 6 to 7. However, maybe not all these seed black holes did grow. Those that did not grow, those that did not become supermassive, should be found in the local universe as relic intermediate mass black holes of in between 100 and 10 to the 5 solar masses, depending on how they formed. So because of this, there has been a search for intermediate mass black holes in different types of sources. It all started in the Milky Way with searching for intermediate mass black holes in globular clusters. But as I'll show later, we will also look for them extragalactic in ultraluminous resources and dwarf galaxies. So let's just start first by globular clusters. As I said, one of the possible formation scenarios for seed black holes is via collisions of stars in dense stellar clusters in the early universe. That's why we expect intermediate mass black holes to be found in globular clusters. So there have been many works applying dynamical black hole models to observations, kinematic measurements, also to pulsar accelerations, in order to infer the presence of a compact object with an intermediate mass black hole mass. And these are some of the candidates that I compiled in the 2017 review. You can see some have upper limits only. And this is one of the most famous cases, omega Cen, for which a black hole mass of a bit less than 10 to the 4 solar masses was inferred, although other works say this is an upper limit and that the black hole should be of even less mass. Another famous case is G1, this one here, which is actually the only globular cluster with some signature of accretion, both from X-rays and radio, as you can see here. Although, again, there are some works that rule out the presence of radio emission. So there's a bit of controversy in globular clusters. Actually, the problem is that in globular clusters, because there's little gas and dust, it's very difficult to find any signature of accretion. That's why we have only, let's say, a few cases in which there's possible accretion signatures, okay? In most cases, we just have a dynamical mass measurement, but no signs of accretion that confirms the presence of an intermediate mass black hole. In the future, with the next generation of radio observatories, we should be able to detect accretion signatures in globular clusters. Another type of black holes that we can find in the Milky Way are wandering intermediate mass black holes. And these are expected because of two reasons. First of all, because in globular clusters, if there's an intermediate mass black hole, this will be ejected due to black hole encounters. And second, because we expect that if a satellite galaxy that has a black hole is disrupted by the Milky Way, the black hole will be found wandering in the halo of the Milky Way. Okay, and this is actually a prediction by Raskov and Malau in 2014. They expect that if seed black holes were common in the primordial dwarf galaxies, so in the first dwarf galaxies in the early universe, and these dwarf galaxies merge to form more massive galaxies, then a population of relic intermediate mass black holes should be found in massive galaxies such as the Milky Way. We can see here some plots of the Milky Way stellar halo, in which we can find many seed black holes formed from population-free stars, so light seeds, but not so many formed from direct collapse. Here, the difference between red and blue dots is whether the intermediate mass black hole is naked or clothed, so whether it has a bound stellar cluster around. And as you can see, the numbers for population-free seed black holes are way higher than from direct collapse black holes. And this is because POP3 stars were thought to be very abundant, while the formation of direct collapse black holes requires some specific conditions, not very common and not very easy to meet. And that's why we don't expect many seed black holes to be formed via direct collapse. These are more recent simulations by Jenny Green, in which they find that around 100 wandering intermediate mass black holes should be present in the Milky Way and with a bound cluster of more than 500 stars. And these wandering intermediate mass black holes should be detectable, according to the simulations, with current observations from Gaia and from the Decals survey. And this is a simulation in which you see possible overdensity. And these are the stars that should be detected with Decals and Gaia. And this is the CMD, the color magnitude diagram, in which they should show some kind of X structure indicative of a main sequence, for instance. However, in practice, what they find is that most of the stars they detect do not belong to a same color magnitude diagram, but most are foreground or background stars. Okay, so they do not find any candidates for intermediate mass black holes wandering in the halo of the Milky Way. With Silvia Bonoli, we have a student now, Julia Unzaga, who is doing a similar work, looking for overdensities in the Milky Way, but now using pan-stars data. And this is one of the images, and these are the stars that he found as an overdensity, plotted in the color magnitude diagram. So this is before cleaning, before removing any foreground and background stars. We see there seems to be some structure. And after we clean, after we remove contaminating stars, we see that the structure seems to be there still. And actually, we can compare this to some known clusters. You see that's the main sequence. Then there are some features like an horizontal branch. Then there are some blue straddles here. So some of these features are seen, for instance, in this other cluster, also found as an overdensity in his code, but not so clear in this candidate intermediate mass black hole. So we conclude that this source could be an open cluster, but it's not clear whether it is an old, a globular cluster, or an open one, whether it can hold a black hole or not. Okay, so it's very complicated to find these wandering intermediate mass black holes in the Milky Way using this method, at least.
Can I just ask a very short question? So why do you need to do this with Gaia at least? Why can't you just get the actual spectroscopic velocities?
Well, first you need to detect the stars photometrically, and afterwards, if these are bright enough, you can apply for spectroscopy. But you cannot directly apply for spectroscopy, right? You need first to look for overdensities based on photometry.
But in the Gaia catalog.
Yeah, so now that we have the overdensity, we will cross-match. Actually, that's something he was doing right this week. He will cross-match with Gaia and check whether the proper motions of the counterparts in Gaia tell you that this is a bound cluster of stars or not. But Gaia is not so deep as pan stars That's why we go first for pan-stars, try to find an overdensity, and any Gaia sources will be located up here. So if we went directly only for Gaia, we would detect like 5 stars, we would be missing this part here. So this wouldn't be cataloged as an overdensity in the code. So first we have to go deeper. Yeah.
How much deeper is pan-stars? Magnitude?
Yeah, I think I don't know if it goes deeper, but down to 22 at least. Yes. And Gaia, I think they stopped around 20.
Okay.
Yeah. So you win way more stars using pan-stars. Yes.
How much of the sky have you covered?
Almost all the sky. So he's been running the code for months now, going through different patches. And I think in the last meeting we had, he said he had covered like 70% of all the pan-stars coverage, but the idea is to do fully. Yes. Okay, so this was for black holes in the Milky Way, intermediate mass black holes in the Milky Way. And now we move to extragalactic intermediate mass black holes, and I'll start with ultraluminous X-ray sources, which is actually how I got engaged to intermediate mass black holes. I started my thesis working on ULXs. Why ULXs? Well, ULXs are supposed to be wandering intermediate mass black holes, such as those in the Milky Way, but in other galaxies. ULXs were discovered as extragalactic off-nuclear X-ray sources with a luminosity higher than that expected from a stellar mass black hole accreting at the Eddington limit. Okay, so we're talking about X-ray luminosities above 10 to the 39 solar masses. Now it has been found that these luminosities could be explained by compact objects such as a neutron star accreting at super Eddington luminosities. However, the very luminous ultraluminous X-ray sources, those above 10 to the 41 X per second, can be explained fully with only super Eddington accretion from a stellar mass object. You need something more massive. So these very bright ultraluminous X-ray sources, extreme ultraluminous X-ray sources, or we call them also hyperluminous X-ray sources, are the best candidates for being intermediate mass black holes. Okay, so sources of between 100 to 10 to the 5 solar masses, but not accreting at super Eddington limits, but at lower regimes. And actually, the very famous case that was discovered already in 2009, I think, is HLX1. You might have heard of this one. Is a source located here in a globular cluster in this lenticular galaxy. The source is very bright in the X-rays. You see 10 to the 42 S per second. So this is at the limit of being an AGN. And also is very bright in the radio. You see here the radio contours in green. So from the radio and the X-ray luminosity, we can use the fundamental plane of black hole accretion and infer a black hole mass. And it was found that the source must have a black hole mass of in between 10 to the 5 to 10 to the 4 to 10 to the 5 solar masses. So in the intermediate mass black hole regime. And also other methods also estimated a black hole mass in this range. So this is actually one of the best of nuclear intermediate mass black hole candidates. We think also that this galaxy underwent a minor merger with a satellite dwarf galaxy, and that the source HLX1 is actually the nucleus of a dwarf galaxy that was stripped in the course of this minor merger. This is a very nice example that we also found some years ago. This ULX is not so bright, nearly 10 to the 40 X per second, and it doesn't have a clear optical counterpart, but you can see here in pink that the X-ray emission, we found that it has also very bright radio emission with 2 peaks here, east and west of the central X-ray emission. This is from the BLA. When we went for BLBI observations, so higher resolution observations, we found that at the position of the X-ray emission, there's compact radio emission. Okay. So again, we applied here the fundamental plane of black hole accretion to derive a black hole mass, and found also something consistent with an intermediate mass black hole. And because of this weird, peculiar structure of the host galaxy, we think that this could also be another case of the nucleus of a satellite galaxy. The dwarf satellite galaxy was stripped in the course of a merger, and what we are seeing is the leftover, the remaining intermediate black hole in here.
And the main galaxy also has an AGN in the center? Or?
Not this one.
Not this one, okay.
But this one, yes. This is another very nice case.
Okay.
There's here clearly a Cipher-2 galaxy in pink, well, purple pink. You can see the radio emission, so it's super bright. There's also very bright radio emission here at the position of the dual X. Note that here the dual X is not very bright as the previous case, but in the optical, we are able to derive a stellar mass, which is consistent with a dwarf galaxy. So we are pretty sure that there was a dwarf galaxy here, and the ULX is located in this dwarf galaxy, and that there's a merger going on. And actually, we also applied for BLB observations, and the radio emission of the ULX, we were able to resolve it into two components. We estimated a black hole mass also consistent with intermediate mass black holes. So this was the first time that we resolved the jet of an intermediate mass black hole candidate. And because the galaxy has possibly undergone a merger, we think that maybe the AGN activity, so the ULX, which is actively accreting, so we can call it AGN, the AGN activity was triggered by the minor merger. We were very interested in cases like this. So with Scott Barrows and Julie Comerford, we applied, we performed like kind of a larger survey for this kind of HLXs.
Could you just back up one slide? So this one, so if those are lobes of a jet, is it in the center, in the middle, where where is it exactly in your opinion?
We think, I think it was the east one. We think that this is actually the core. So we don't think these are two jets, so two jets, one on one side, but that one of them is the core, and we see only one-sided jet.
Oh, okay.
But it's very difficult to say because we don't have more information than this. But we concluded that it had to be this way. Yeah, I think it was this one.
That's the X-ray center or not, or that's the radio.
The thing is that
you say that E is the
because we had for this we had two frequencies here. You see, we had 4 gigahertz, and then the black contours are at 7 gigahertz.
Okay.
So we can derive the spectral index, and if it's flat, you can say it's the core. The thing is that the resolution of this is way higher than that of the X-ray. And now I'm not sure where the X-ray position falls exactly, but we concluded that this one here had to be the core. So we wanted to find more sources like this. So what we did is to cross-match the Chandra source catalog, which is a catalog of, let's say, all the X-ray detections found so far, and this is archival data, with the SDSS, the Sloan Digital Sky Survey. We did that applying a threshold for offset. So we wanted to find sources, X-ray sources, which were offset from the galaxy center, because we wanted to look for ULXs. And also we applied a cut in luminosity so that we found hyperluminous X-ray sources. We didn't want 10 to the 39 X-ray sources, but bright ones, above 10 to the 41, so that they are HLX. And we found more than 100 sources that you can see here. So this is the host galaxy, and this is the position of the HLX. In SDSS, this is pan stars, and here we have the Chandra pixels. And in many cases, you can see that we are able to detect in the optical the host galaxy of the ULX. Sometimes not in the SDSS images, but we can in the pan-star images. So these are potential galaxy mergers, as in the previous cases. So cases of a dwarf galaxy being merged by the major galaxy, by the more massive galaxy. What we did is to apply for HST time and time also with the Grant-Tecan. We wanted first to detect the stellar counterpart. In some cases, we have it for around 50 cases, but we want to study more the stellar counterpart, try to derive the stellar mass, check if it's a dwarf galaxy or not, and also try to see any signatures of merging activity that confirms that these ULXs are located in a dwarf galaxy that merge with the bigger galaxy. This is important because we can test the merger-driven intermediate black hole growth then this can have important implications for understanding seed black holes in the early universe. We have been assuming that local intermediate mass black holes are the relics of the early universe seed black holes, if these haven't grown and haven't been touched or affected by accretion or mergers. But if we find that there's growth of the primordial seed due to mergers, then things change. And I'm going to talk more about this later on. So now we move to most of the projects I've been working on for the last years, which are intermediate mass black holes in dwarf galaxies. Why in dwarf galaxies? As I said before, we expect to find in the local universe the leftovers of those seed intermediate mass black holes that did not grow. And there have been many simulations trying to understand what's going on with these seed black holes. This is pretty old, from 2010, but there are more recent papers in which they show that this still holds. We have two main formation scenarios, as I said before, direct collapse and pop-free stars. Because pop-free stars are thought to have been very abundant, if seed black holes form via this mechanism, we expect in today's dwarf galaxies, so galaxies, let's say, below 100 kilometers per second in stellar velocity dispersion, we expect a high black hole occupation fraction. So if seed black holes from pop-free stars, we expect to have many dwarf galaxies today with an intermediate mass black hole. Okay? While if seed black holes from via direct collapse, which, as I said, is thought to have been a less common mechanism that requires special conditions, then we expect in today's dwarf galaxies a lower black hole occupation fraction. So we don't expect many dwarf galaxies today to host intermediate mass black holes. And an imprint on the different seeding mechanisms can be also found not only in the black hole occupation fraction, but in the M sigma correlation. Remember that I said before that for supermassive black holes, there was a tight correlation between the stellar velocity dispersion and black hole mass. Okay, so this is above 100 kilometers per second. Now, if we go to the low mass regime, to dwarf galaxies, and seed black holes formed via pop-free stars, we expect to find here a population of undermassive black holes. While if they form via direct collapse, we expect to find a plume here, a bending of the M sigma correlation. Okay, so studying the black hole occupation fraction and the M sigma correlation in today's dwarf galaxies, we could infer how seed black holes formed in the early universe. And apart from this, dwarf galaxies are the best places where to look for the intermediate mass black holes because of the following. First of all, because we think, or we thought until very recently, that dwarf galaxies are regulated by supernova feedback. This means that stellar winds can eject the gas from the center and prevent the growth of the black hole, of the intermediate mass black hole. Also, dwarf galaxies have low mass, have low metallicity. So these are the galaxies that best resemble the first galaxies formed in the early universe. Okay, so if these are the galaxies that best resemble the primordial galaxies that hosted the intermediate mass black holes, and these intermediate mass black holes did not grow because of supernova feedback, there was no gas available for the black hole to grow, then we should find the relic of the early universe intermediate mass black holes in today's dwarf galaxies. So there have been many searches for intermediate mass black holes in dwarf galaxies. And here I'm just citing some of the works. Most of them focused on using optical and infrared emission line diagnostics, such as this one here. This is called the BPT diagram. We have the ratio of two emission lines here and other two here. And depending on where your galaxy falls in this diagram, you can infer whether the ionizing emission comes from an AGN or from a star formation or from a mixture of AGN and star formation. Okay. Using this method, together with the detection of broad emission lines, we have found hundreds of candidates of intermediate mass black holes for which we can have the black hole mass from the width of these broad emission lines. However, this is all based in the local universe, so below limited to redshift 0.3. The black hole masses, because we use broad emission lines, cannot be very low. We can only detect black holes of 10⁴ to 10⁶ solar masses. And also this is biased against very luminous very luminous AGN, not very luminous such as massive galaxies, but very luminous in this regime, so that we can detect them, because dwarf galaxies are fainter than massive galaxies. So one thing that we can do to prove the presence of accretion of intermediate black holes in these dwarf galaxies is to go for X-ray observations. And this is one of the very famous cases in which we have broad emission line from a black hole here at the center, from which a black hole mass of around 10 to the 4 is determined. We also have X-ray emission, and we have also the EPD diagram. So this is one of the most famous galaxies, dwarf galaxies, in which we have an AGN, an intermediate mass black hole, which is actively accreting. What happens in these dwarf galaxies is that many of them have lots of star formation. Okay, so when we use optical diagnostics such as these ones with SDS data, SDSS means that you have a single fiber here centered at a 3-second radius at the center. It can happen that because of a strong star formation, or if the host galaxy light is also very strong, the AGN signatures are missed, are diluted by application of these single fiber spectroscopy observations. Okay. Also, if you have an AGN that doesn't sit at the center where you have located your fiber, but is off nuclear, for instance, due to mergers, or because it's wandering, the intermediate black hole is wandering the galaxy, then you will also miss it by using these central aperture observations. To overcome this, what we did is to go for integral field spectroscopy, such as the MANGA survey, in which rather than having a single aperture here, you have more than 100 fibers that cover the whole galaxy. So in each of these positions, you have one spectrum. Okay. By doing that, in the VPD diagram I showed before, rather than having only one point, as you would have with the SDSS, you would have only this gray square here. You see many spaxels. You have one spectrum per each pixel in your galaxy. So you can infer whether the ionizing emission comes from AGN, star formation, or is composite across the entire galaxy. And actually, in this case, for instance, that's very nice. We find that most of the emission at the center comes from AGN, while at the outskirts, we have more of star-forming ionization. Okay. Okay, so that's the case of a central AGN that it would also have been detected with the SDSS. But then we have cases like this one, in which the SDSS would have missed the source or would have classified it as composite, not a clear AGN, while we see that there's lots of spaxels with AGN emission that we see here and here. So this could be either an AGN that is obscured here at the center because of the presence of star formation, or it could be an AGN that it's switched off. So we can see the light echoes of the last burst of ionization, but currently the AGN is no longer active. And another nice case is this one here. This one would have been completely missed by SDSS because, as you see, it's classified as a star forming. However, we do detect some spaxels which are ionized by an AGN, and it could be that the AGN is off nuclear here, or again, that because of star formation, we are missing the emission from the AGN because it's dominated by star formation. So in total, using MANGA, we find 23 new AGN in dwarf galaxies that had been missed by previous searches. Another nice thing is that the volumetric luminosity of this AGN is very low. It's actually way fainter than that found in previous surveys, also in X-ray and radio. Okay, so using IFU, integral field spectroscopy, we find not only a hidden population of AGN, but also of very faint AGN in dwarf galaxies. And one of the nice discoveries of the paper is that one of the sources presented broad emission lines that you see here in H alpha. So from this broad component here, from the width, which has more than 100 kilometers per second, we can estimate the black hole mass. And we find a black hole mass of around 10 to the 5 square masses. So consistent with an intermediate mass black hole. Okay, so this is the first type 1, this is a type 1 AGN because it has broad lines. This is the first type 1 AGN that has been discovered using integral field spectroscopy, and that was hidden before in previous observations. Okay, this was all for the optical, but then, as I said, using optical emission and ratios, optical searches, we are limited to very nearby sources. One thing we can do is to use X-ray surveys to go farther away, and there have been also many works on that, tens of candidates discovered up to redshift 0.6. But if we want more sources, and we want to go to higher redshifts, if we want to derive the black hole occupation fraction, remember, so that we can infer how seed black holes formed in the early universe, then we have to go to deep surveys, large surveys such as Cosmos. This is something we did back in 2016 and 18. In Cosmos, we have more than 2 square degrees covered by all major telescopes on Earth and in space. So we have hundreds, thousands of galaxies that for which we select those with a stellar mass below 9.5 in log. So these are dwarf galaxies. That's the typical cut, the threshold we apply for selecting dwarf galaxies. Of these more than 50,000 dwarf galaxies that we find in Cosmos, we have a richness of photometric properties. So we have star formation rate, we can have photometric redshift, the stellar mass, and we can have X-ray emission. We have Chandra X observations. However, of these more than 50,000 dwarf galaxies, only 40 are detected in the X-rays. You can imagine how few are actively accreting, or at least that we can detect. And these 40 X-ray detections are shown here. This is X-ray emission, and this is the X-ray emission expected from star formation. So the problem of dwarf galaxies is because these are fainter than most massive galaxies. The X-ray emission that you detect might not come from a black hole, might not come from an intermediate mass black hole. It might come from stellar processes. So you have to remove the contribution from star formation before concluding that there's an AGN in there. So that's what we did. The solid line here shows what would be the expected X-ray luminosity from star formation from X-ray binaries. And we see that all our sources are way above this 1-to-1 correlation. So we conclude this must be AGN. We estimate a black hole mass below 10 to the 6 solar masses, so consistent with intermediate mass black holes. Another nice thing is that although it's photometric, we go out to redshift 2.4, which would be these sources here. So this is the highest redshift we found in back then, 2018, for AGN in dwarf galaxies. Because we had many sources up to high redshifts, and we have an X-ray survey that we know how much complete it is, we can derive the AGN fraction corrected for completeness. And we can do that in 2 stellar mass beams that I'm showing here in pink and blue. And you see here the 2 stellar mass regimes, finding that the AGN fraction decreases with stellar mass. Now, this is AGN fraction, not black hole occupation fraction. Okay? Black hole occupation fraction might be way higher than AGN fraction. Yet, we see that this decrease of AGN fraction with stellar mass is consistent with what it is expected from simulations of direct collapse black holes, in which we see that the black hole occupation fraction also decreases with stellar mass. Okay? So this indicates that most likely seed black holes form via direct collapse. But of course, there can be a bias here towards more massive black holes, these direct collapse black holes being easier to detect than population 3, lighter black holes. That was in the X-rays, but the last couple of years has seen a blossom of also radio searches for these AGN in dwarf galaxies. And this is because AGN in dwarf galaxies also have radio jets. And these are 2 nice examples, a bit old now, but in which we can see extended emission from AGN. This is the famous case I showed in the beginning, which had X-ray emission, broad emission 9. You see, it has also radio emission. So just 2 years ago, Amy Rines performed a search for AGN dwarf galaxies using the radio, using the VLA. After removing the contribution from star formation, which can be also very important here in the radio regime, Rines et al. Found 13 AGN dwarf galaxies in the radio, and this is one of them. You can see very compact VLA radio emission. For this source, Molina et al. Applied shock models and concluded that the emission had to come from a relatively inefficient accretion flow. and that due to shocks, the surrounding medium could be ionized. So this is telling us that there could be significant radio feedback in AGN dwarf galaxies. Now we know that in massive galaxies, radio jets are able to hamper or trigger star formation. So it would be very nice to investigate what's going on in dwarf galaxies, whether AGN feedback is also significant, because so far we had been assuming that dwarf galaxies were dominated by supernova feedback, that supernova winds expelled the gas from the center and prevented the growth of the black hole. So to study AGN feedback in dwarf galaxies, we need to go for larger samples, at least to have something statistically significant. So we did that using, again, the Cosmos survey, but now the BLA, the radio coverage of the survey, which, as you see, is pretty deep, an RMS of 2.3 microyansis per beam. Again, we removed the contribution from star formation, and as a result, found more than 30 radio AGN dwarf galaxies that you can see here distributed in redshift. Although this is photometric, we see that we reach a redshift of 3.4. This is a super high redshift for an AGN in a dwarf galaxy compared to optical surveys that were limited to 0.3, 0.5. The nice result of this work is that the jet powers and the jet efficiencies of the radio AGN dwarf galaxies are as high as in massive galaxies. Okay, and we know that in massive galaxies, radio jets impart significant feedback that can impact the host galaxy. This is another more recent work from Davis. This time they use the LOFAR survey. They don't have such a great sensitivity, but yet they detect 78 radio AGN dwarf galaxies, for which they find also jet powers very large, okay, as in massive galaxies. So these are all similar works, different works that point to a similar conclusion, which is that AGN feedback can also be very significant in dwarf galaxies, triggering or hampering the star formation and thus the amount of material available for the black hole to grow. Okay, so it's not only supernova feedback, but it seems that AGN feedback is also playing a role in dwarf galaxies. This is another work from Bradford. Here they are using H1 observations. In the y-axis, we have the ratio of observed to expected H1 gas. And this is the distance from the BBT. So here it's a star forming, and as you move here to the right, we have AGN emission. And what they found is that sources which tend to be more AGN-like have lower gas. So this is suggestive of AGN feedback destroying or having consumed the cold gas, the cold H1 gas. So again, possible evidence for AGN feedback. All these results are in line with the actual detection of outflows in dwarf galaxies in AGN, like the ones I'm showing here, in which Liu et al. And also Manzano King find asymmetries in the O3 line profile of more than 1,000 kilometers per second, which are indicative of the presence of outflows. So we have some evidence for AGN feedback in the optical, in the radio, in spectroscopy. And also very recently, this is just from 2 months ago. This is Hennis 210, one of the first dwarf galaxies in which an AGN was found based on the detection of X-ray and radio emission. The candidate AGN is located here, and these are radio contours overplotted on the H-alpha HST image. And just 2 months ago, Schut and Rines found that there's a filament that we see here in this optical image, also somehow here, connecting recent sites of star formation, which would be here. Okay, and this filament, they modeled it with a bipolar outflow model. Okay, and this was published in Nature, as I said, I think in February. So they found evidence for AGN feedback triggering star formation, not preventing star formation, so not negative feedback, but positive feedback, okay, triggering star formation.
This galaxy is similar to the Large Magellanic Cloud in mass and... Yes,
actually, that's how we apply the stellar mass threshold. we use 9.5 in, as I said, in log, and this is the mass of the LMC. Yeah. So let's go back to our sketch of seed black holes forming here at high redshifts. Some can grow, become supermassive, and power the quasars we detect at redshift 6 to 7. And those that did not grow should be found in the local universe, as leftover intermediate black holes in dwarf galaxies. Okay. Now, what happens if we have feedback and mergers affecting the growth of these intermediate black holes? It could be that a 10 to the 5 intermediate black hole found here is not the relic of a direct collapse, but is actually a POP3 intermediate black hole that has grown with time. Okay, so it could be that supernova feedback is not hampering black hole growth, but that AGN feedback and also mergers trigger, enhance black hole growth. And if this happens, then local intermediate black holes should not be treated as the relic of the early universe seed black holes. Okay. So the question that arises is, are intermediate black holes in local dwarf galaxies the relics of the early universe seed black holes or not? So are they untouched or have they grown due to mergers and feedback? To investigate this, we can do two things. One of them is to further study AGN feedback and mergers in the local universe. The other option is to go to redshifts as high as possible and try to directly detect these seed black holes. As I said, the highest redshift AGN dwarf galaxy we have found so far is 1 at 3.4 from the VLA coverage of the Cosmos survey, but this was photometric, so you have some uncertainties there. However, just an email from last week from Haiwon Su, we found that in the sample from the Cosmos survey, there's at least one source at a redshift almost 2 with a spectroscopic redshift. Okay, and that's a very high redshift, spectroscopic for a dwarf galaxy with an AGN. Another work that we are doing right now is looking for this high redshift AGN in dwarf galaxies using the Vipers survey. And what we do here, because we have a multi-wavelength coverage from optical to UV, infrared, X-ray, radio, we are applying an SED and spectral energy distribution fitting with different components. We have an AGN accretion disk, also the galaxy, and then an AGN dusty torus. And then we estimate the stellar mass, apply a probability distribution function, and check which would be the upper limit for that stellar mass for that galaxy. And then we apply a cut. Okay, we select those galaxies we have an upper limit below 10 to the 10 solar masses, can be classified as dwarf galaxies. We do that for more than 1,000 broadline AGN, so sources that have broad emission lines. And of these more than 1,000 broadline AGN, we find 22 dwarf galaxies. Okay, 22 dwarf galaxies which have broad emission lines in different lines because we have many redshifts from less than 0.4 to 2.7, as we can see in here. Okay, this is a work that has been recently submitted. The other option we have to go to high redshifts is to wait for the next generation of observatories. Here we can have the James Webb, of course, which would be able to distinguish between population 3 and direct collapse seed black holes at high redshift based on the photometry, as we can see here. We can also have X-ray observatories detecting direct collapse black holes at redshift up to 10, with masses of in between 10 to the 4 and 10 to the 6, depending on whether you have the Athena X-ray observatory or the mission concept links. One case very interesting at very high redshifts is this direct collapse black hole candidate, CR7, which stands for Cosmic Redshift 7, because this was a Cosmos survey source detected at redshift 6.6 as a very strong Lyman alpha emitter. For this source, we have an estimated black hole mass of 10 to the 6 solar masses, an estimated LX X-ray luminosity of more than 10 to the 43. So, because we have X-ray luminosity and we have black hole mass, we can apply the fundamental plane of black hole accretion to try to estimate the radio flux that this source would have at this high redshift of 0.6, sorry, of 6.6. And we do that for different fundamental plane correlations from different authors that you see here in different colors. Okay, this is the expected flux from CR7 applying this fundamental plane correlation. This is the frequency. And I'm overplotting here. These are different sensitivities of different surveys, like the next generation BLA or the SKA final survey, the SKA mid survey. And what we find is that when comparing to the expected emission from H2 regions, we find that below 3 gigahertz, the SKA final survey should be able to distinguish between direct collapse black holes, so between the flux of that we are estimating from the fundamental plane, and the flux of an H2 region, or also from supernovae. Okay, so we should be able to detect radio emission from a direct collapse black hole like this with the SKA final survey. Another thing that we can do is to investigate which is the mass that direct collapse black holes should have at high redshift so that we can detect them with surveys such as the SKA. We did that. We have here direct collapse black hole mass across versus redshift, and for different fundamental planes of black hole accretion, which is how we estimate these black hole masses. And we find that direct collapse black holes of around 10 to the 5 solar masses should be detectable with the SKA at redshift 8. At higher redshift, we should be able to detect slightly more massive black holes of 10 to the 6 to 10 to the 7 black holes, solar masses with the SKA. Okay, so we see that direct collapse black holes could be detected at birth with the SKA final surveys, and this would allow us to prove the formation of pathways of the first supermassive black holes, or the first quasars in the early universe.
Can I just quickly ask, so you can't detect them, but do they exist?
When we detect them, maybe I can answer that.
No, but from theory, do we have any hints that, I mean, it seems very extreme to me at redshift 20, right? The 10 to the 7, or maybe, I don't know.
Okay, the ones doing the simulations can tell me whether they can form already at redshift 20.
Yeah, I mean, I don't think we can say yes or no, but I think it's more interesting to do that than that, because, you know, redshift 8, I think it will never be conclusive, because you could also have a top 3 black hole that has enough time to grow to that mass, right? You would not take 6 times 10 to the 5. Redshift 8 is not so extreme. You could get a top 3 seed that grows even below Eddington, but close to Eddington, maybe 0.8 Eddington. You might get to that mass, right? By redshift 8. Mm-hmm. So I think in order to be conclusive on the direct collapse, we really need to go very high redshift, like 15 at least.
So I think this would be more interesting.
Yeah, definitely, because I mean, at 8 or 10, I'm sure you can get some top 3 seeds to grow. I mean, if you're super Eddington accretion, even if it's older.
Mm-hmm.
But you can cook up a model at redshift 20 with direct collapse that produces your 10 to the 7 solar mass.
If direct collapse happens as some of the models postulate, it's not supermassive stars forming at very high masses. It might have. I mean, actually 20 is a bit high, because I think the current models, they usually give formation as slightly lower redshift, right? I think it's usually a redshift 15 to 10. That 20 is a bit on the high side. But I think there are enough uncertainties there. I don't know.
Well, the point is that you can detect it at 20, we can detect it at 15 as well.
Yeah. So I think, you know, going down to less than 10 probably it will not be conclusive. Mm-hmm. So it's better to go higher and be surprised. But
sorry, can I just, what's the 500 megahertz there?
The frequency of the observations.
So these are low, these are like redshifts like 2, right? So that's where.
Redshift 2?
Is it SKA, right? 21 cents.
Yes, okay, so we compute this for different frequencies, and I'm showing here the 500 one. But
okay, so these are observations that like local, not at 20, I mean.
No, okay, yeah, no, but we have already applied the rest frame conversion, and so this would be the frequency at which we should use, the radio interferometer. Okay, you should take the radio telescope, and at 500 megahertz, you should be able to detect this or this. Yeah. Because the fundamental plane of black hole accretion, okay, is usually at 5 gigahertz. Okay, we have made already the conversion. Yes, and that's why we are showing here 500 megahertz and not 5 gigahertz.
But that is assuming that they are accreting at some editor ratio. What's the assumption in the luminosity?
Yeah, in principle, the fundamental plane just comes. I mean, you just need X-ray luminosity, radio luminosity, and black hole mass. So you play with these 3 variables. Yeah. But it's true that in principle, the fundamental plane should be applied for sub-Eddington accreting sources.
Sub-Eddington accreting.
Yeah. That's also why we try different correlations, because different authors provide different slopes. Yes. Yeah. Yeah. Okay, and then of course we have also gravitational waves. We know there has been already one detection of an intermediate black hole of 140 solar masses coming from the merger of 2 stellar mass black holes. And actually such light black holes should be detectable currently already below 10 to the 3. We should be able to detect intermediate mass black holes. If we want to go to higher masses, 10 to the 5 solar masses, then we should wait for LISA. And the nice thing is that LISA will prove a similar mass redshift regime as the SKA, for instance, or of X-ray surveys performed like with LINX. So we have seen that SID intermediate mass black holes are required to explain the formation, the detection of the first supermassive black holes at high redshifts. In the local universe, the relic intermediate mass black holes that did not grow should be found in globular clusters, for which accretion signatures might be detectable in the future with radio observatories. Also, as wandering intermediate mass black holes in our galaxy in the Milky Way, here we expect tens of intermediate mass black holes to be found with a bound cluster of stars. And extragalactic, we can find intermediate mass black holes as ULXs, as ultraluminous X-ray sources, and as AGN in dwarf galaxies, which we can detect up to redshift 3 with large and deep surveys, for which we can derive the AGN fraction, finding that it's consistent with that from direct collapse black hole formation models. However, we have seen that mergers and AGN feedback might yield significant growth of the SID intermediate mass black hole. So we have to take that into account and further study the role of AGN feedback and of mergers in growing intermediate mass black holes. And finally, we've seen that with the next generation of observatories, we should be able to directly detect SID intermediate mass black holes at birth, such as at redshifts 15 or 20. So that's it, and thank you very much.
Questions? Lawrence.
I have a couple of questions. The first one is, maybe I missed something, but you were talking about some sort of structure that would be formed in a magnitude color plot. If a globular cluster also has a intermediate mass black hole in it, and could you maybe tell me why?
Yeah, well, that's not related to having a black hole or not. That's what you expect from stellar evolution. That's a color magnitude diagram. And you expect stars to form a main sequence, and then there's a red branch. So this comes only from stellar evolution. It's not related to having a black hole, but you expect wandering intermediate mass black holes to have a bound cluster of stars. And of course, because these are not actively accreting, that's the only way you can find them by detecting this bound cluster of stars. That's why try to find overdensities, stellar overdensities, and investigate the stars that we find and whether they are indeed in a cluster, so forming a cluster. Yes.
I see. So you're using them to hope that maybe there's also a black hole.
Exactly. But that structure that you mentioned is not related to having a black hole or not. I mean, we find it in clusters that do not have a black hole. Yes.
And you mentioned that in simulations, you find that there should be actually several hundred in a Milky Way galaxy. But I didn't really understand if you would have expected to already have found them in the Milky Way, or if sort of limitations in the...
Yeah, you expect to find them. They should be detectable.
So it's weird that they have not been detected.
But in practice, we don't detect them.
Okay.
Yes.
So what could be happening here?
Well, yeah, that's a good question, because so the simulations, let me see. Yeah. They find that they should be detectable with Gaia and decals. Okay, so these are all simulations. Okay, you do not only expect to have these wandering black holes, but you expect them to be detectable. You know, that's the result of their work, and you expect to find something like this. And you see, this is Gaia. As I said, Gaia goes over here. With decals, you should go deeper and detect these ones here. Why in practice you find this instead? So you have only like 6, 7 stars and not something as nice as this. I'm not sure. Maybe it's not so easy to find these overdensities. Also check, because many of these sources, as you see, might be foreground, background stars. In practice, yeah, it's not so easy.
What simulations did, because I mean, Jenny is an observer, so she should probably use the simulations of another group to.
Oh, I should check the paper. I don't know if the simulations are from her.
I'm curious to see what exactly.
Yeah.
Because of course, if you change the occupation fraction, you know, the numbers can go anywhere.
Would you say it's more likely that there's something wrong, for example, with the model, or more that the observations have been unlucky?
I think it's more that the observations are not good enough, or at least the method. Because when we go to pan stars, which is what my student is doing, he does find where more stars.
Okay.
I guess it depends on the survey you are using. So pan stars, I think it's a bit deeper than decals. So I think it's just a matter of time before we find these candidates.
Okay.
Yeah, I was also wondering about the magnitude limit here. I don't know in these bands like what Euclid would reach, but is it deeper? Like they have
Euclid?
Yeah.
But Euclid isn't it more extragalactic?
But you would
this kind of stars
too, right?
Okay.
I'm just wondering if you've checked the magnitude limits, because it wasn't in your future surveys.
Yeah, we have been checking.
It is all sky, and you should.
That would be nice.
See, I can't remember offhand. Remember what the magnitude limit in these bands are. Sure. I'm not an observer, so
No, because we have, I mean, work like this has been done with the SDSS, with decals, so the Destiny Legacy surveys. This is pan stars. We check also the Hypercam Subaru survey. So yeah, the more surveys we can check, the better. So yeah, we can also check how deep Euclid goes. Thank you.
Pedro, first of all.
Yeah, can you go to your 2019 cartoon?
Mm-hmm.
I'm trying to understand. So for obvious reasons, you're and the fault, exactly this. So you're basically trying to understand what is the relation between the AGN occupation fraction and the black hole occupation fraction in your opinion?
Well, the AGN occupation fraction is just the fraction of black holes that are actively accreting. So of course, it's lower.
Yeah.
It's not observational
bias. You
bias.
can say about this.
No.
Right. Okay. So because then that means that you could have a very large population of black holes that never grew, and those are the real relics.
It could be, but you don't detect them.
But you're biased, because you're observing the currently accreting ones.
Yeah. But also it could be that those are not currently accreting, but they were somehow in the past, right? So
for that, you have to go to higher lecture.
Yeah.
Couldn't we look just at the central stars of like the Magellanic Cloud and do the same thing than in the Milky Way? Is this completely out of reach?
Sorry, say it again.
Well, trying to find S stars in other galaxies, is this, you know, in local dwarf galaxies?
You mean these overdensities that for these wandering black holes? No.
Well, I was just wondering whether, because there should be one in each dwarf galaxy, essentially, right?
Mm-hmm.
And we have loads.
Actually, many of the AGN in dwarf galaxies are found off nuclear, are not sitting at the center. So this.
Oh.
Yes. Also because in dwarf galaxies, sometimes it's not so easy to define a center. So many are found, yeah, wandering already.
But in the LMC, they tried, right? They didn't find. I mean,
LMC, there's no AGN.
Yeah, there is no evidence.
Yeah. Well, it can be that it's not active and then we don't detect anything. Yeah.
But even if they are off nuclear, they should have a little, you're talking of the S stars of the Milky Way.
Exactly.
They should have a little cluster around them. So, but I don't know if it's something.
But of course, if in the Milky Way we are struggling to find this bomb cluster of stars, if you go beyond the Milky Way, I mean.
Well, we have found them 20 years ago, so maybe. I don't know, I have no idea.
Yeah, but first we start with the Milky Way, and then we'll see.
Thomas.
Very nice talk. Just a quick question about your off-center black holes. So you said that they have probably mergers, right? Do you have any signatures or any hints that there might be an active or a black hole at all in the center when you have one off-center, like a signature of two?
There are very few cases, maybe I can think of one, for an active black hole in the main galaxy and then also active one in the merging dwarf galaxy.
Okay, so there is a candidate at least that you have two black holes.
Yeah, so actually one of the ULXs I showed is like this, right? The main galaxy is a Cipher-2, and then you have the active black hole, which is the ULX in there. But it's not, yeah, it's very uncommon to find this.
Sorry, I think maybe I misunderstood, but is there some kind of degeneracy between the luminosity and the mass of the black hole? Like if you detect a high luminosity, then you say that, okay, there may be superintern, but not too superintern. So we just say that the mass of the black hole is intermediate. But what's the reasonable highest luminosity you put in the model? Like?
Yeah, you can produce the high luminosities, for instance, of ULXs. You can produce high X-ray emission by having a low mass object accreting at super Eddington rates, or by having a higher mass object accreting at sub Eddington rates.
But when you say super Eddington, is like 10 times m dot Eddington or 100 times?
Super Eddington, it depends. For me, super Eddington is above 1, a ratio above 1, and sub Eddington is like 10%.
Okay.
But so 10 to the minus 3. But it depends.
The issue is that I think, as you said, that these diagrams, these correlation diagrams, they really are not meaningful if you assume an accretion flow that is not the standard sub-Eddington accretion flow.
Yeah.
They wouldn't make any sense, basically. So that's a problem because you can't really extrapolate to.
Yeah, because you don't know whether
they would
accretion was super Eddington or not by then. Yeah.
So yeah, so we're just checking. It's AB magnitude limit is 24.5.
Okay.
And that's for the all sky, and then the deep survey is, I think I recall, 27 or 28.
Wow, thank you.
So
that's very useful.
That's interesting enough.
Yeah.
Yes, yes.
No, that's right. Another.
If it's all right.
Okay.
Okay, so if I remember correctly, even in this slide, you mentioned that that some dwarf galaxies have AGN feedback that is 100 times more energetic than the binding energy of the gas. But and then you said that this could be a hint that they could grow significantly by the time they are formed to now. Is this what you were saying?
Yeah. So the idea is that AGN feedback can be positive and negative. So it can prevent star formation or trigger star formation. Okay. So because it's affecting the amount of gas, so star formation, the amount of gas available for the black hole to grow, it can be that it hampers black hole growth or that it triggers black hole growth. And actually, so this is this recent case of triggering of a star formation, okay? So positive feedback. So it could be that you could also be triggering black hole growth. So it's all a matter of the amount of gas available at the center.
Wouldn't a very, very strong episode of AGN feedback in the long run hamper black hole growth because you get rid of all the gas?
Yeah, actually there are cycles. Yeah, there are cycles. So you have AGN feedback, maybe you can have as a positive or negative, but in case it's negative, you expel the gas. So at some point, the AGN cannot be active anymore. It switches off. And then because it's switched off, gas can go back to the center again. It triggers AGN activity again. The AGN is again active, it expels gas out again. So yeah.
As usual, it's complicated to say how.
Yeah, there's a duty cycle.
Yeah. Okay.
Yes.
Yeah, but the jets are peculiar, right? Because here the triggering, I guess, is because of the jet, right? I guess that's the picture that you have one side of the jet that is pushing the gas, increasing the density,
exactly,
and triggering. But if the radiative feedback itself instead would be normally always suppressive. I guess it's dependent on which mode is dominant.
Yeah.
Because I guess you had in mind this probably that you tend to eat up and suppress.
I would imagine that I was thinking about the link of AGN feedback and how quickly it grows, because of course while it's doing these jets, it's eating gas, but I was wondering in the long run, if you get rid of all the gas, then you don't grow. So maybe AGN feedback is actually showing that you wouldn't grow that much if you have so much of it. It's a bit weird, but
self-regulation. I mean the self-regulation.
Yes.
Yeah, that's one idea.
Yeah, so my point here was that it's not only supernova feedback expelling gas so that the black hole cannot grow. There's also AGN feedback, and this AGN feedback cannot be only negative but positive. Okay, so we shouldn't be taking it as granted that supernova feedback is expelling gas so the black hole doesn't grow. It could be that there's more going on and that the black hole does grow.
How is that picture evidence for this, for positive feedback?
Well, because they connect this filament here, they connect it with this site here of a star formation.
Or it could also just go off like this and actually prevent star formation top and top.
No, because the filament, this one here, is what they model as an outflow. Okay, this outflow corresponds to this filament.
They know in which direction it's going.
Yeah, so this comes from a spectra taken at different points in here.
Sorry, stupid question. Why is it sinusoidal? I don't really get it.
Oh, I don't know the details. I don't remember.
Okay.
But yeah, okay, this is a jet model, right? So it's jets are helical structures.
Okay.
Yes.
It must be the phase of the jet or something, I guess. I don't know.
Typical helical models are used for describing jets.
Maybe one more question.
I'm sort of wondering again about trying to detect the black holes and dwarf galaxies. We're trying to do, say, CO dynamical mass measurement. Is that a way forward to maybe when it's not an ADM, try and constrain black hole masses or when they do see something?
Yeah. There are some dynamical mass measurements using ALMA, for instance, or near infrared observations, high resolution observations, but done for a few, let's say, 5 sources, very nearby and bright AGN dwarf galaxies. For the rest, you cannot do.
Okay, so it's also.
But it has been done. Yes.
For everything else.
And you can. For many cases, you have a black hole mass upper limit, but in others you can model. But it has been done for a few cases.
Okay, so let's thank Matt again.